Hello everyone, my name is Dr. Tarkeshwari Verma from CSV2. I welcome you in this MOOC course of Fundamental of Engineering Physics. Today's topic is the superconductivity and contains our introduction, history, types of superconductor, their different phenomena like Meissner effect, critical temperature, etc. And also today we will discuss about the application of the superconductors. Let us start the introduction part of the superconductor or superconductivity. Those material exhibit the superconducting properties that known as the superconductor, and that phenomena known as the superconductivity. Superconductivity refer to the phenomena where a material exhibits zero electric resistance and the expulsion of the magnetic fields when cooled below the certain critical temperature. This state allows the critical currents to flow identically without energy loss, which has profound implication for technology and science. A superconductor is a perfect conductor of the electricity. It carries direct current with 100% efficiency because no energy is dissipated by the resistive heating. Once induced a superconducting loop, direct current can flow undimnished forever. Superconductor also conduct alternating current, but with some slight dissipation of the energy. Superconductors are different from ordinary conductors such as a copper. Unlike regular conductor, whose resistance gradually reduces, the superconductor resistance drop to zero below a fixed temperature with a critical temperature. At this temperature, a superconductor can conduct electrically with no resistance, which means no heat, sound or other form of energy would be discharged from the material when it reaches a critical temperature. To become superconductive, most material must be incredibly low energy state. That means that is very cold. Presently, excessive energy must be used in a cooling process, making superconductors uneconomical and inefficient. A study is underway to design components that become superconductive at a higher temperature. Let us explore the history of superconductor materials. In a year of 1911, the phenomenon of superconductivity was first discovered in 1911 by Dutch physicist Huig Oens at the University of Leiden. Oens was studying electrical properties of the materials at a very low temperature. Particularly near absolute zero, he discovered that mercury exhibited zero electrical resistance when cooled below 4.2 Kelvin. This marked a first observation of the superconductivity, a state which material conduct electricity without any resistance. Meissner effect, that discovered in 1933 in a German physicist Walter Meissner and Robert discovered that superconducting material expels all magnetic field from its interior when it transitions to the superconducting state. This phenomenon, known as a Meissner effect, was a key experimental observation that distinguished superconductor from perfect conductor and provide critical clue for the developing theoretical explanation. In 1957, John Barden, Leon Cooper and Robert developed the first successful microscopic theory of superconductivity, known as a BCS theory. That BCS theory named after their initial. The BCS theory explained superconductivity in a term of Cooper pairs. Pairs of the electron that move through the superconductor without resistance due to alternative interaction mediated by lattice vibration, which is known as the phonons. The BCS theory was significant breakthrough in a condensed matter physics and the trio of Nobel Prize Physics in 1972. In a periodic table, various number of superconductors are presented. Some are popular like tin, mercury, lead. They have superconductivity in a like 3.72, 4.15, 7.19. There are some superconducting material are also available. First is the NBTI, second is the NBSN. Superconducting material have two types of basis of their temperature, high temperature superconductor and low temperature superconductor materials need to cooled cryogenic temperature in order to exhibit the property of superconductivity. The difference between a high and low temperature superconductor can be best explained using the figure 1. This graph explains the complete loss of the resistance to the flow of electricity through wires and a LTS material. And at a critical temperature Tc, which is the differ from the each superconducting material. The specific material high temperature superconductor material in this chart is no electric resistance below the 108 Kelvin as they oppose the specific low temperature material in this chart, which is no electrical resistance below the 10 Kelvin. For general properties of the superconductor, first is the electrical resistance. Let us understand the normal electronic resistance. Electrical resistance is a normal conductive material. Electrical resistance is a measure on the opposition of the flow of electrical current. It arises due to collision between the free electrons and the atom of the material, leading to the energy loss in the form of heat. Ohm's law. From the most conductor, the relationship between the voltage, current and resistance is given by Ohm's law, V is equal to IRV. Here resistance, Ohm's law, the relationship between the voltage, current and resistance is given by Ohm's law. Here the resistance remains constant over in a range of the voltages and temperatures for the normal conductors. Electrical resistance in a superconductor. Zero resistance below critical temperature. When the material becomes superconductive below its critical temperature, the electrical resistance drops to 0. That means that electrical current can flow through the superconductor without any energy loss. In the superconducting state, the current can be circulate in a loop of the superconducting wire indefinitely without any applied voltage. This is the stark contrast to normal conductor where resistance always causes energy dissipation. Behavior across the critical temperature. The critical temperature is the temperature at which a normal state of the conductor changes to the superconducting state. Different superconducting material have different critical temperatures, which depends on a physical and chemical properties. For instance, conventional superconductor like mercury have a close to the critical temperature close to the 4 Kelvin, while high temperature superconductor can have critical values above 77 Kelvin. Role of impurities in a superconductor. Impurities are foreign atom or electric element introduced into the superconducting material. They can affect the material in several ways. Before we discuss the role of impurity, we should know what is the Cooper pair. In a superconductor material, the temperature below critical temperature, electrons, which are generally fermions, known as the Cooper pairs. This pairing occurs due to attractive interaction mediated by lattice vibrations, known as the phonons. When electrons move through the lattice, it distorts a lattice structure, creating a region of positive charge and attract another electron. This interaction can lead to the formation of pair of electrons with opposite spin and momentum. Now continue with our topic, role of impurities. Dispersion of the lattice structure. Superconductor typically have well ordered lattice structure that facilitate to pairing of the electrons. Impurities can be dispersed this lattice, which in turn can interfere with the electron pairing mechanism. The dispersion can scatter the Cooper pairs, making a header for them to from there maintain their coherence. Scattering of Cooper pairs. Impurities can cause scattering of Cooper pairs, leading to increased resistance in pure semiconductor. Cooper pair can move through lattice without resistance. When impurities are present, they scatter these pairs, thus increasing like the breaking of pair apart, which affect superconductivity. Reduction of critical temperature. A primary observation effect of the impurities in a decrease the critical temperature. This is because the lattice dispersion and scattering effect causes a reduction in the density of state at the Fermi level, alter the electron phonon coupling, which is the crucial for the superconductivity. The higher the concentration of the impurities are more pronounced this effect become. Impurity effect is the different superconductors. Type 1 superconductors materials show a sharp transition to the superconducting state like a usually pure element superconductor. Type 1 superconductor. These materials show the sharp transition to the superconducting state and are the usually pure element superconductor. Soft superconductor are those which can be tolerate impurity without affecting superconducting properties, also called the soft superconductors. Only one critical fixed exists for this superconductor. Critical field value is very low, exhibit perfect and complete Meissner effect. The current flow through the surface only. This material have limited technical application because very low field strength values. Type 2 superconductor. These are usually alloy or complex compound, also is known as the hard superconductor. Hard superconductor are those which cannot be tolerate impurities. That means impurity affect the superconducting properties. Two critical fields are presented here, SC1 and HC2. SC1 denoted as a lower and HC2 denoted as a upper form. This critical field values very high, don't exhibit the perfect and complete Meissner effect. It is found the current flow throughout the material. These material have wide technology of very high field strength values. Next is the affecting parameter is the pressure and stress. Both pressure and stress are the powerful tool for the tuning the superconducting properties of the material, but the effect are highly dependent on the specific material or end condition. Pressure increases can sometimes increase the critical temperature of superconductor by altering the material lattice structure and electronic properties, enhancing electron phonon interaction or including favorable phase transition. Stress can have varied effect on critical temperature. while it might increase critical temperature in some cases by changing lattice parameter or enhancing electron interaction. It can also decreases critical temperature if it introduces defect or disorder of the superconducting state. Next is the isotope effect. Isotope effect in the critical or the transitions temperature value of the superconductor is found to vary with the isotopic mass. That means the transition temperature is the inversely proportional to the square root of isotopic mass of the single superconductor. The isotope effect in a superconductor involves changes in the critical temperature when isotopes of the element are substituted. This effect is primarily due to interaction between the electrons and phonon, with heavier isotopes generally leading to lower critical temperature and lighter isotope leading to a higher critical temperature. While the isotope effect is well described by BCS theory in a conventional superconductors, its behavior is a high temperature supercomputer is less clear, indicating the complexity of the superconducting mechanism in this material. Next is the effect is the magnetic field effect. If a strong magnetic field applied to the superconductor below its critical temperature, the superconductors undergoes the transition from the superconducting state to the normal state. Critical magnetic field. The maximum magnetic field of the superconductor can withstand before losing the superconducting properties. Exceeding this field causes the superconductor to revert to a normal state with the electrical resistance. Next is our topic is the critical current. The maximum current is the superconductor can carry without losing superconducting state. Beyond this current, the material transition to a resistive state. Both parameters are crucial for defining the operational limits and superconductor in the practical applications. Next our topic is the Meissner effect. The Meissner effect is the fundamental characteristics of the superconductors, where they expel magnetic field from their interior when they transition into the superconducting state. This effect is the crucial for understanding the unique behavior of superconductors. Here the detailed explanation are presented. The Meissner effect occurs when the material upon the cooling below the critical temperature enter in a superconducting state. They actively expel magnetic field from its interior. This results in the superconductor becoming perfectly diamagnetic, meaning it exhibits zero magnetic permeability and repels external magnetic field. Mechanism of the Meissner effect. First one is the superconducting transition. When the material cooled below the critical temperature, its transition from the normal state where it behaves like a typical conductor or an insulator to superconducting state. In this state, the material not only loses their electrical resistance but also exhibit the Meissner effect. Repulsion of magnetic fields. In a normal conductor, when exposed the magnetic field, the field penetrates the material and induces current that current their own magnetic fields. However, when the material becomes superconducting, it expels the magnetic field from its interior. This is because of the superconducting electron generate current that exactly cancel out the applied magnetic field inside the material. The superconductor becomes perfectly diamagnetic, meaning that the magnetic susceptibility of the material is -1. This complete explosion of the magnetic field is the key feature of the distinguished superconductors from ordinary conductors. Quantization of magnetic flux. In a type 2 semiconductor, when a magnetic field penetrates the material, it does so is quantized unit called the flux quanta or fluxon. Each fluxon carries a quantum of magnetic flux phi 0, which is the fundamental constant given by phi 0 is equal to h by 2e, where h is the Planck constant and e is the elementary charges. Importance of the Meissner effect. Distinguishing the semiconductors. That effect one of the defined characteristics of the superconductors. It help differentiate the true superconductor from the perfect conductor, which would allow the magnetic field to remain trapped inside even the material had zero resistance. That Meissner effect has also some applications that has practical implication in the technologies such as the magnetic levitation and the construction of sensitive magnetic field detector. The Meissner effect is the phenomena where superconductor explain the magnetic field. Next our topic is the BCS theory. BCS theory named after John Barden, Leon Cooper and Robert. It is the foundational theory of the explain the phenomena of the superconductivity in conventional superconductors. Developed in 1957, it provides the microscopic understanding of how and why material can conduct electricity without resistance at a low temperatures. BCS theory explains the superconductivity in conventional superconductors. It posits that at a low temperature electrons from pair called the Cooper pair, which move through the lattice without resistance. This pairing occurs due to attractive interaction mediated by phonons, the vibration of the crystal lattice. BCS theory also predicts an energy gap in the electronic structure, preventing scattering and thus ensuring zero electrical resistance. The theory occurs for the key phenomena like Meissner effect and isotopic effect, providing a comprehensive explanation for how and why superconductors behave a way they do not low temperatures. Mathematical framework for this phenomena. Wave function and Hamiltonian. BSS theory involves the complex mathematical framework where the Hamiltonian of the system describes the interaction between the electrons and phonons. The wave function of the superconducting state is the many-body wave function that describe all the Cooper pair in a material. The BCS ground state wave function can often refer a BCS state in a superposition of the state with the different number of Cooper pair, reflecting the collective behavior of these pairs. Energy gap equation is also this theory lead to an equation that describe the energy gap as a function of its temperature at a absolute 0 is the maximum energy gap and it decreases as temperature increases, vanishing the critical temperature. Understanding the superconductors, BCS theory provides the comprehensive explanation of the superconductivity. Superconductivity is the most conventional superconductors such as the elemental metal like tin and mercury that have also application in a technology. That understanding of the superconducting provided by BCS theory has lead to the numerous application including the development of the superconducting magnets, MRI machine and the potential use of the quantum computers, but that have also some limitation. BCS theory primarily applied in a conventional superconductors. It does not fully explain high temperature superconductor where other mechanisms might be involved. The search for the theory to explain high temperature superconductors remains active area for the research. BCS theory is the foundation theory of the condensed matter physics that explain how A superconductivity arises in conventional superconductors. It describes how electron from Cooper pair leading to the macroscopic quantum state with the zero electrical resistance. Superconductors have the wide range of application due to their unique properties such as the zero electrical resistance and the expulsion of the magnetic field. Here some key applications are presented. First is the magnetic resonance imaging. We are also known as the MRI. Superconducting magnets are used in a MRI machines to produce a strong and stable magnetic field, which is the essential for the creating detailed image of the body internal structure. The strong magnetic field provided by the superconductor allow the higher resolution imaging, improving diagnosis accuracy. Second application is the maglev trains. Magnetic levitation trains use the superconducting magnets to lift and propel the train without physical contact with the tracks. That have one benefit, this reduces friction, allowing the higher speed and smoother ride, while also reducing the wear, the tear on the tracks. Particle accelerators. Superconductor magnets are crucial in a particle accelerators like a Large Hadron Collider, where they use a guide and accelerate the particles to near light speed. That strong magnetic field generated by the superconductor enable precise control the practical beams, essential for the high energy physics experiment. Power transmission. Superconducting cables can be transmit electricity with the virtually no loss of energy, making them ideal for efficient long distance power transmission. They reduce energy losses and improve the efficiency of the power grid, which is especially important for the interacting renewable energy source. Superconducting quantum interfaces devices is also one of the famous application of the superconducting material. They are extremely sensitive magnetic field sensor used to the various application, including medical diagnosis and geological survey. Their ability to detect tiny magnetic field makes them invaluable in the field in a high precision. That have ability to detect tiny magnetic field also. Next application is the fault current limiters. Superconducting fault currents limiters are used to power grid to protect equipment from the damage due to sudden surge in a current. They respond quickly to fault condition, reducing the risk of damage and enhancing the stability of power grid. Next, our application is the quantum computing. Supercomputers are used to quantum computers to create qubits, the basic unit of the quantum information, because they can maintain quantum state with the minimal energy loss. Next, our application is the magnetic levitation. Superconductors are used in a magnetic bearing and flywheel energy storage systems, where they allow for the frictionless efficient operations. This technology enhances the efficiency and the mechanical system by reducing wear the energy loss. Next, our field is the research and development. Superconductors are used in a various research application, including the study of the fundamental physics, material science and the development of new technologies. They enable high precious experiment and the exploration of new scientific phenomena. Our next field is the application field is the medical diagnosis. We are already discussed the MRI system. A part of this, there are some another equipment are also available like NMR, nuclear magnetic resonance. This allows the invasive and detailed analysis of biological sample in a medical research and diagnosis. Superconductors are crucial in advancing technology in a field of medical diagnosis and transportation to energy and quantum computing. There are unique property enable to application that require storage, strong magnetic field, high efficiency and driving innovation across the multiple industries. So dear learner, hope so you understand today's lecture very well. Today we have learned about the introduction about the superconductor, Meissner effect, their application. Thank you.